Hello everyone and welcome back to Clear Creek Solutions hydrology education videos. In this video we're going to cover rainwater harvesting and give you an explanation. So rainwater harvesting is the practice of capturing rainfall from rooftops or other surfaces, storing it and reusing it for beneficial purposes. It's one of humanity's oldest water management techniques, and today it's seeing renewed importance as communities look for sustainable solutions to water supply and stormwater challenges. By collecting rainfall at the source, we can reduce the demand on potable water systems, lower stormwater runoff, and provide irrigation or even indoor potable uses. So in this presentation, we'll cover what rainwater harvesting is, the key system components, its benefits and limitations, and how engineers represent it within stormwater design. By the end, you'll see why harvesting rainwater is both an ancient practice and a modern green infrastructure strategy. So rainwater harvesting is the process of collecting rainfall where it lands, most often from rooftops, and diverting it into storage containers like cisterns or tanks. Depending on treatment, the stored water can be used for non-potable applications, such as irrigation, toilet flushing, and cooling, or with advanced filtration and disinfection for potable use. In addition to supplementing water supply, rainwater harvesting has a dual stormwater benefit. By capturing and holding water, it reduces runoff volume and peak flows, which in turn reduces flooding and erosion pressures on local systems. So rainwater harvesting is not a new idea. It has been used for thousands of years. Ancient civilizations from the Middle East to South Asia built cisterns and step wells to store in rainfall during wet seasons for use in dry months. In arid regions today, rainwater harvesting is still critical for survival. What has changed in modern times is its role in urban areas, where stormwater challenges and climate variability has made harvesting an important green infrastructure practice. Cities are now encouraging or even requiring rainwater harvesting as a way to reduce both water supply stress and stormwater impacts, making it a practical climate resilience tool. A basic rainwater harvesting system includes 5 components. First, the catchment surface, typically a roof or occasionally a paved surface. Second, the conveyance system, gutters and downspouts that move water to storage. And third, a first flush diverter that directs initial dirty runoff away from storage to improve water quality. And fourth, the storage unit, which can be above ground tanks, underground cisterns, or modular systems. Fifth, treatment and distribution for non-potable uses. This may be as simple as a filter and pump. And for potable uses, full disinfection is required. Together, these parts create a reliable, small-scale water supply and stormwater control. Rainwater harvesting provides multiple co-benefits. It directly reduces demand on municipal or well systems, saving potable water for where it's truly needed. For homeowners and businesses, it provides a dedicated irrigation source, reducing utility bills. From a stormwater perspective, every gallon captured is a gallon that doesn't contribute to runoff, which means less flooding pressure and reduced erosion downstream. On a larger scale, widespread adoption supports sustainability goals, enhances resilience to drought, and builds redundancy in community water supply. Now, let's discuss the limitations and challenges. And despite its benefits, rainwater harvesting has some definite limitations. Storage is finite. Once tanks are full, excess water overflows as runoff. Rainfall patterns can be variable, especially with climate change, so harvested supply may not always match demand. Water quality is another concern. Untreated rooftop runoff can contain bacteria, debris, or chemicals, so systems require filters, diverters, or treatment for safe use. Maintenance is needed to keep gutters clean, check pumps, and manage take conditions. Finally, regulations will vary. Some regions encourage harvesting, while others restrict potable use without specific approval. In modern stormwater planning, a rainwater harvesting is considered a green infrastructure practice. By capturing rainfall at the source, it effectively reduces impervious area. Systems with first flush diverters help manage initial pollutant loads. Storage provides a detention function, holding back water and releasing it later through controlled use or overflow. Many stormwater regulations allow credit for rainwater harvesting toward flow control or water quality requirements, as long as the design meets local standards for storage volume and usage assumptions. Now let's discuss its use in WWHM, the Western Washington Hydrology Model. In WWHM 2012, rainwater harvesting is explicitly modeled as a best management practice. Engineers enter the tank volume and the intended water use pattern, such as daily irrigation withdrawals. The model runs continuous rainfall data to estimate how much water is captured, stored, and reused, how much bypasses as overflow. Regulatory credit is only given if harvested water is assumed to be regularly drawn down. A tank that stays full provides no stormwater benefit. This ensures compliance with the Stormwater Management Manual for Western Washington, which requires conservative assumptions for that credit. In EPA-SWMM, rainwater harvesting systems are represented using the cistern LID control. Users define the tank capacity, surface area, and outlet configuration. SWMM allows optional drawdown curves to simulate daily water use, which controls how much storage remains available for new storms. Overflow from the cistern can be routed to other drainage system elements. By assigning cisterns to subcatchments, engineers can test how much stormwater is captured and how harvesting changes hydrographs, peak flows, and downstream system loading. Rainwater harvesting can be applied at multiple scales. At the residential level, it's often used for garden or lawn irrigation. In commercial buildings, cisterns provide water for cooling systems or toilet flushing. Industrial sites may use harvested water for processes that don't require potable quality. Farmers often integrate rainwater harvesting into supplemental irrigation. At the community level, district-scale systems can capture large roof or pavement areas and supply neighborhood irrigation or graywater systems. The versatility of harvesting makes it one of the most adaptable stormwater practices. Successful design requires matching expected water demand to likely supply. Engineers calculate how much roof area is available, local rainfall depth, and expected usage, then size the cistern accordingly. A first flush diverter is recommended to improve water quality. Overflow must be safely directed to infiltration or drainage when tanks are full. Maintenance plans are important. Gutters and filters must be cleaned, pumps inspected, and tanks managed for debris or mosquito control. When these elements are considered, harvesting systems perform reliably over decades. So these are the works referenced, and to summarize, rainwater harvesting captures rainfall where it lands, provides water for irrigation and non-potable uses, reduces stormwater runoff, and can even help meet regulatory stormwater requirements. Down below, you can get access to our free EPA-SWMM course by clicking the link in the description. This gives you access to our 24 free video series that can teach you how to use EPA-SWMM at a basic level. If you have any questions, please leave a comment down below. We thank you so much for watching, and anyways, we will see you next time.